famous mathematician called Peter Montgomery in 1985. And as mathematics papers go, it was, of course, 3 pages, and it cited an incredible amount of time. And what did Montgomery do? What was Montgomery's insight? Montgomery found a way to do modular multiplication, which costs somewhere around a regular multiplication. So instead of costing like a division, it costs approximately like a regular multiplication, which is really cool. But the rules are you need to go into Montgomery representation, Montgomery's domain. So you have to take your numbers and you have to switch. You have to enter Montgomery's world. And this is an operation, costly operation. And then you do math in the Montgomery representation. In the Montgomery representation, multiplication is very easy. And then you have to leave Montgomery representation. That is, again, a little expensive. So this costs a step. But if you're doing thousands of multiplications, you pay one reduction in the beginning to enter, one reduction in the end to leave, and in the middle, it's a regular cost of multiplication. So obviously, a 3-page mathematics paper is not very easy for me to teach from. But fortunately, Hank Warren, who is an engineer, you don't need, I'll show you. I'll show you about the Montgomery reductions. They're really, really fascinating. I'll show you. So there is an engineer called Hank Warren, who is he wrote like a book about cool algorithms called Hacker's Delight, and he wrote a very, very nice description of the Montgomery reduction. And in 2012, you can find it on the middle. I'm going to explain it from there. It's pretty self-evident, but just like math, you might like to watch it offline. So this is Montgomery reduction, as explained by Hank Warren from Hacker's Delight. There we go. So this is a general sketch. I want to do g to the power of e modulo n, and I want to do it very cheaply. So what is g to the power of e? It's just g times g times g times g. Lots of multiplication. So I'm going to start with g modulo n. And then I am going to enter the Montgomery representation. And then I am going to do the exponentiation in the Montgomery representation, g times g times g times g times g. I'm going to do this e times. And now I have g to the power of e in the Montgomery representation. And then I am going to leave the Montgomery representation, and the result is going to be the regular g to the power of e. And the idea is that entering and leaving the Montgomery domain are a little expensive, but these operations in the middle are cheap. So if I have enough of these modular multiplications, in the end, I will save a lot of time. So is this cool with everybody? This is Montgomery representation. Fine. Okay. So you're asking what is the representation? So the representation is another number in the multiplicative group. It is another number which represents g. And the operations you do on this number are cheap. It's all going to be explained. Okay. It's not very intimidating. Let's say it's 35–40% intimidating. There are more intimidating things in the course. Right. So now I want to show you the Montgomery reduction. I won't be giving any proofs. I will be skipping some stuff, but you can read the Hacker's Delight. Why is this faster? It's faster because so each one of these multiplications in the Montgomery representation is nearly as fast as a regular multiplication over the integers. It's equivalent. It's costs as much as a multiplication, whereas a modular multiplication costs as much as a division. So this is much faster. Multiplication instead of division. The modulo is, there is no modulo. It's awesome. There is no modulo. I'll show you. So how do I do Montgomery reduction? So the first thing I need to do is I have to get another variable to work with, and this variable is R. So I'm moving back to the shared notes. So I'm going to do Montgomery. Let's put this down. So I need to choose. So let's start. What do I have in the beginning? I have M, which is a message. I have S, which is the signing key. And I have N, which is a public module. Cool. Now I need to choose a value R, which is easy to use. And this value has to be just a number which is larger than N, and it's easy to do math with. So everybody chooses a large power of 2. Well, what does a large power of 2 look like? So let's say if the public modulus is, I don't know, the multiple of 2 prime numbers, I don't know, 23 times 37. It's 7. So I'm going to choose R. So I'm going to take a large power of 2, which is so I'm going to choose R to be 2 to the power of 10, which is 10,024, which is more than 851, and it's equal to 1, 2, 2, 2, 2, 2, 2, 2, 2, 2. I think doesn't really matter. This is a number. So why am I saying that this number is easy to use? In what sense is it easy to use? So how do I multiply by R? How do I multiply by R? I shift. Perfect, I shift. How do I divide by R? Now I also shift, right? I shift to multiply and I shift to divide, which is very, very cool, very, very cheap. How do I take the remainder modulo R? How do I do that? Think about it. Bitwise and thank you, Dimitri. So I'm going to, yeah, that's correct. Oh, yeah, let me explain it if you don't see. If I have a number, another number, and I want to find the remainder of division by this, I just zero out all of the significant bits, and the result is modular reduction modulo R, which is very, very fast. All of these operations are practically free compared to multiplication, and of course, a fortiori compared to modular reduction. So now I need to enter the Montgomery representation, and to do that, I just multiply by R modulo N. That is the magical step of entering Montgomery representation. And as you see, this requires 1 modular reduction. Now, A is a member of the multiplicative group. I'm claiming that A times R is also a member of the multiplicative group. Why can I claim that? Does anybody have an idea? Why is A times R inside the group? Why didn't I run away from the group by doing this? No guesses? Okay, so the answer is that R is 2 times 2 times 2 times 2 times 2, right? This is a large power of 2. And obviously, 2 is inside the multiplicative group. Why am I sure of that? Because n is a multiple of 2 large primes, and primes are usually not even numbers, they are odd numbers, and definitely 2 does not divide neither p nor q. So, is everybody here convinced that a times r modulo n keeps me inside the group? Does anybody here need extra convince? So you're all convinced that a times r is inside the multiplicative group modulo n. Fine. So I have some of you are less convinced. Let me convince you once again. If A is closed, if the group is closed under multiplication, as I told you in the last meeting, every 2 elements I multiply from inside the group, the product stays inside the group. So A is inside the group because this is what I told you, and 2 is inside the group because 2 does not divide neither P nor Q because P and Q are both odd. So A is a member and 2 is a member. A times 2 times 2 times 2 times 2 times 2, as many times as you like. So it's going to stay inside the group. The group. Okay, the group is all of the numbers which do not have a common divisor with n. So n is p times q, two prime numbers, and I take all the numbers between 1 and n minus 1, which do not have a common divisor with n. It's called the z star sub n. Awesome. So now I have Montgomery of A, and I call it A underscore. And now to calculate A times B, I want to A times B is going to be A times B times R modulo n. But the problem is if I multiply A underscore times B underscore, I get A times B times R times R. You see, the R goes twice. Is the group commutative? I think so. I think so. I'm not sure. I'm not sure. Don't go into it. We're not going there in this course. Please, have mercy. It's difficult enough as it is with the COVID that you don't have to have abelian and commutative and stuff in the course. Have mercy. So A times B, A underscore times B underscore is not Montgomery of A times B because they have R twice. So I need to do A times B divided by R, and all this modulo n. So far I didn't help anyway. I didn't help in any way my operations because it still looks to do this. I have to do A times B, and I multiply R minus 1. I can calculate it using how do you call it? Extended GCD. It's very cheap to calculate. But this is still looks like I need the modular reduction. But then this is the genius of Peter Montgomery, which is explained in the lecture notes. This is actually equal to this fantastic looking formula, which also doesn't look very helpful for us. But let's look at this number once again. A times B multiplication over the integers. So far, so good. A times B times n, again, multiplication over the integer. Pretty cheap. Modulo R. How do I do modulo R? Do you remember? That's just an and. Okay, so modulo R is very, very cheap. Again, multiplied by n. This is another multiplication over the integers. And I take all this magical stuff and divide it by R. How do you divide by R? I shift right. This is a free operation. And so A times B plus this whatever, this calculation, which is quite cheap to calculate, is equal to Montgomery of A times B. Nice, so what? Well, Peter Montgomery proved that this number is never greater than 2 times n. And this is the genius. This number, this entire thing, is between 0 and 2 times n. So, why do they have an n? So Montgomery of A is defined as A underscore. Okay. So the genius of the Montgomery reduction is that this number is known to be between 0 and 2n minus 1. So my modular reduction, thank you there. My modular reduction, if I know the number is between 0 and 2n, how do I do a modular reduction? I subtract, I compare, and subtract. Okay? I compare and subtract. Subtracting is very, very cheap. It's incredibly cheaper than multiplication. It takes a very small amount of time. And of course, it takes much less time than division and remainder. So the range is between 0 and 2 times n. There's a beautiful, the Hacker's Delight. I put it in the Moodle. You can read it. It's very, very readable. It's written by an engineer for engineers to read. So, and it is a delight to read. So don't be worried about it. So as a result, in the Montgomery representation, instead of doing an expensive modular reduction, we do a very, very cheap subtraction. Oh, okay. I'm okay if you want to. I don't know. Is it that delighting? I didn't look at the other parts of it. Only at the introduction, which was very exciting, and only at this part. I think it's like an ASCII file, right? With this ASCII art with stars and stuff like that. Okay. So if you want to be a delighted hacker, read the Hacker's Delight, and it will be very cool for you. Okay. So I'm going to turn on the shared whiteboard, and I'm going to ask you to circle the word which is most exciting for you as a hacker on this slide. A single word. Please circle the word which, as a side channel attacker. Okay, right? Yeah, okay. So yes, indeed, right. So the exciting word is sometimes, or if. Thank you. Very, very nice use of advanced teaching technologies here. Awesome. So yeah, okay. Put down your pens. I'm finishing. Okay, right. I'm done. Thank you. Very insightful. The most problematic word on this slide is if. If means that the computation is going to depend on the secret. And if means that the execution time is going to depend on the secret. And this means that we're going to be able to do the timing attack. So really, really cool.